So the two graphs you just made were distance graphs. Distance versus time. So what does the graph itself tell you? If it's a distance graph, well, obviously distance. Now, key math word, slope. The slope of the graph tells you the velocity. So when we were doing the remote control car and it was speeding up, and I had you draw that curve of best fit, what can you tell me? What's happening to the slope? It's getting steeper. So since the slope is getting steeper, that meant the velocity is increasing, which makes sense. It was accelerating. It was having greater and greater and greater velocity. Eventually it reached max speed, so it kind of evened out. But slope means velocity on a distance graph. All right, and something else we'll also do is try to describe the motion in words as if it were something that represented a car. So, for example, a distance graph, and I have a distance question. You always want to look at your question and look at what type of graph it is, because we won't always just do distance graphs. But looking at it, what is the distance at 3 seconds?
Meters.
Perfect. Take.
Hey, what is your shirt?
Mason, not the time. Now, what's the velocity at 3 seconds? You have to find slope. It says velocity. What is velocity? And it's not velocity graph. That would actually be really easy. If it was a velocity question, velocity graph, it would be as easy as part A. But this is where you have to remember that means slope. So how do you do slope? Now, if your line has a shape, you actually have to pick points on the line segment that you're talking about. Yeah. Point. Pick 0, 0. Always. Overrun. Sign 2. You know, I can say going here, okay, I go rise, I go up 6 over 3. Or using these points that I've picked, y2 minus y1 over x2 minus x1, I 2. You could, in this case, don't always think you can do that. You can do that because 0, 0 is one of your points. Up 6 over 3. We'll see an example that will not work. Just be a little careful about finding slope. Make sure the points you pick are appropriate for your line. All right, in words, this is a car. What's the car doing?
Speeding up at a time.
Staying the same speed.
Staying the same speed.
Good job.
This is like the second graph in that lab, or in this control car thing.
5 and 1. How do you get 10 and 2?
Speed is going up.
I picked these random points.
Okay. Wait.
10 was the y, x was the 5.
Will we have to pick our own?
You will have to pick your own points. And you could have picked any. I just picked those. Okay, so the car is moving at a constant velocity. Constant velocity is a term I like to see, if appropriate. And that's it. It doesn't do anything else. Move at constant velocity. All right, next. Here's another distance graph. Okay, first question. Distance at 3 seconds. So distance question, distance graph. Just line it up. It's still 6. Okay. Velocity at 3 seconds. No. Yes. This is a case where you can't just say, okay, 3 seconds right here. I'll just say 6 and 3. Those are my points, so I'll just say 6 divided by 3. No, because if you're saying 6 divided by 3, you are implying that you started at 0, 0. But not to get here.
Okay.
So we can pick any points we want, but they have to have the same slope. So they got to be on this line. So I can pick these two, or But I should just be able to tell, yeah, and I don't even have to pick a point at 3 seconds. I could. I just like endpoints because sometimes that's easier to see on a graph. But, you know, think about rise over run. What is your rise from this point to this point? 0. So look out for horizontal lines. Flat lines, automatic. So what is this car doing?
This one's same.
It just stopped.
From here to here, it's doing what?
It reaches its max.
The same speed. And now this is where this is not completely realistic. You can't be but that's what this graph says. Constant speed, constant stop. To show that it would slow down, you have a little where just out. But we're just the math easy and avoid curves. So according to the graph, it says the car is going at a constant velocity and then somehow magically just stops. Yes? Even in the process of hitting a wall, there would have to be a little slowdown. Well, just a little bit. Just a little curve right there. All right, so far so good. Now, all right, same graph. Distance question, what's the distance at 1 second? Right? What's the velocity at 1 second? Pick any points that are appropriate to, 3 seconds is here, so any points on this line segment are fine. Don't pick this point. This point has nothing to do with this slope. Now you could have just picked 3. Here this would have been fine, because you go from the origin straight there.
How do they get that so easily?
The rise I picked, like from red to red, you go up 6 over 2, or you say go up 3 over 1,
And the slope is there.
or of course into this slope formula. However you'd like, you should get through.
How many more we got?
I don't know.
We got 4 more.
4 more. Moving. Okay. So this was all distance graphs. Now, what if it's a velocity graph? Which we have not done any of those yet. We didn't draw those. All of those were distance graphs. So this time, if it's a velocity graph, velocity info should be easy. Just look at it. Good.
Yeah.
This time, slope is not going to mean velocity. Slope meant velocity on a distance graph. If it's a velocity graph, an increasing slope on a velocity graph would mean, your speed is increasing. You are accelerating. You're speeding up. So acceleration will be the slope. Okay, so we'll do these questions the exact same way. Just realize it's a slightly different graph now. Okay, so now it's a velocity graph. Now, just skip down here. I'm going to ask you, if this is a car, what's the car doing? Very good. Common mistake. Just because you see a flat line doesn't mean something is still. It did on a distance graph. On a distance graph, it means, okay, my distance is 10, my distance is 10, my distance is 10, I'm not moving. But on a velocity graph, it means my velocity is still 10. My velocity is still 10, so I'm just moving at a constant rate. I am moving here. But come to 10 seconds, what does the car start to do now? Accelerate. Very good. All right, anyway, what's the velocity at 5 seconds? Perfect. 10 meters per second. Okay? don't be thrown because we just did a whole bunch of slope for velocity and try to slope. It is a velocity graph. Just look at it. It's 10. Question will be the acceleration. Of course, it's a flat line. We can pick our points. We can write all that. But, rise over run, there is no rise. So there is no acceleration here. And then you guys just told me that part. Constant velocity, then it accelerates at 10 seconds. We have 2 slides left? We're going to make it. We're going to make it. All right, you guys are writing, try to just abbreviate, say constant velocity, then accelerates. Slightly different questions. Great, 30 meters per second. And how about acceleration at 20? Let's see if we can figure this out before I put the numbers up.
Very hard here.
30.
Hearing some 2s. Great. All right, pick any points on this line, even though I'm talking about 20. And you can, of course, pick that point, but I like endpoint. So rise over run from here to here. Please do not pretend like you started at 0, 0. Don't accidentally think that and try to do 30 divided by 20. If I start here, I go up from 10 to 40. How much? From 10 up to 40, I go up 30. From 10 over to 25, 15. I go up 30, over 15. Slope. I could have picked a smaller example, like you could have done right here. I go up 10 over 5.
I did the 6 over 3 thing. You count 6 like that.
Well, be careful of that because that's, these are scaled. That just happened to work because these were each incremented by 5. Be careful doing that. And so, in summary, graph, what's the easiest information you can pull off of that? Distance. Vice versa. Get off the velocity graph. Velocity. But what is the slope? Acceleration. But all right, I made it through.